Okay, it's all working properly. So we continue on with the session. Next speaker is Mohamed Meguebel from University of Saclay, Sorbonne, Paris, and also Instituto de Física Fundamental. And yeah, all yours, Moha.
Buenas tardes a todos y todas. Thank you for the introduction, and many thanks to the organizers for having put this event together. So before getting started, I would like to thank dearly the research group in which I've been working, and more specifically these three researchers, so Guillermo, Juanjo, and Adrián, without whom this project wouldn't have been possible. So let's cut to the chase and try to give some insights on what quantum links are. So as you are probably already aware, one of the many limitations that quantum computers are currently facing hardware-wise comes about when scaling them up. And one way to bypass this issue and still be able to expand the computational power of these systems is to connect them with a so-called quantum link, which is essentially a waveguide down which a photon is going to propagate. Now, this project has laid emphasis more specifically on superconducting qubits. And if one is to understand this kind of system, one first has to get a grasp of the general quantum circuits model. So to do so, let's consider the bread and butter of the circuits model, which is the LC circuits, which you are already very familiar with. And there is actually some sort of an analogy between this electrical circuit and a general, traditional harmonic mechanical oscillator, for which the momentum of your mass is going to be equivalent to the charge of the electrical circuit, and the magnetic flux is going to match the position of that mass. Which is why, in order to quantize this circuit, we can just lay out the standard quantization procedure. So defining your conjugated variables, phi and charge, so the magnetic flux and the charge, which enables you to compute your classical Hamiltonian, which you make quantum by defining these two operators, which are to fulfill this commutation relation. So again, very akin to the standard mechanical oscillator, for which you then end up with a quantum harmonic oscillator Hamiltonian of this form. Now, the catch is that, as I've said, working with qubits, and to do so, one has to isolate a two-dimensional subspace, 0, 1, and unfortunately, a standard quantum harmonic oscillator fails to do so, which is where the superconducting part steps in, because there is a specific superconducting device called a Josephson junction, which is going to introduce a small anharmonicity across your energy spectrum, enabling you to isolate a two-dimensional subspace, which is going to correspond to your qubit computational subspace. Further, now that we have the general framework of the quantum circuit model, we now have to better understand how your waveguide within your quantum link is going to interact with an apparatus, so a qubit or a cavity. And to do so, we consider a quantum optics model. So in this case, the James-Cumming Hamiltonian, which can be written down as this form in the case of a cavity coupled to a waveguide, where you see that you have a free term for your Hamiltonian and a free term for your cavity and the interaction terms. So as I was saying, for this kind of Hamiltonian in quantum optics, it is typical to consider what we call the ohmic bath hypothesis, for which your coupling strength is going to evolve as the square root of your frequency. But as you can see, there is a pitfall, which is that it would mean having a coupling strength diverging, which is why it is routine in quantum optics to enforce an ad hoc ultraviolet cutoff. Nevertheless, the issue is that the choice of this cutoff is salient when it comes to important physical properties of our system, such as the decay rate, which is why it stands to reason that one has to find a rigorous derivation from the circuit model down to a quantum Hamiltonian and hopefully find a coupling strength which does exhibit a natural cutoff frequency. So let's do just that by considering your waveguides connected either capacitively or inductively to a network of magnetic flux degrees of freedom. So this abstract box is essentially just your qubit or your cavity. And it so happens that in the case of TE-AIM modes waveguides, you actually have a rigorous map from the electromagnetic model to a circuit model with the corresponding linear dispersion relation. The issue is that for the waveguide of interest, which is the rectangular waveguide, this kind of modes are not physical, and you wouldn't be able to have your wave propagating down your waveguide. So, which is why we have to rely instead on a more physical waveguide, which is the TE waveguide, for instance. But instead of seeking for a rigorous map from this electromagnetic model to a circuit model, we chose instead to manufacture a circuit inspired by the previous one by adding a supplementary inductance, which leads to this nonlinear dispersion relation with an additional mass-like term, which I call gamma, which is a gap in the wave vector. So doing your traditional classical electronic equations, in this case the conservation of current, you end up with this wave equation, which is a simple D'Alembert equation with an additional mass term and two boundary conditions at both ends of your waveguide. So at 0, the coupling point, and at L. Now, the next step would be to consider a traditional separation of variables in time and in space. And if you put back in this expansion into this set of equations, you end up with this problem in the spatial modes UN. And pay attention that we have introduced alpha and beta, two length parameters over which we are going to have some degrees of freedom over, because regardless of their choice, this problem remains a generalized Storm-Liouville problem for which an expansion theorem holds. So this is why next the rest of the calculation is merely the same standard quantization procedure as before, slightly more complicated because now instead of having only 1 degree of freedom in magnetic flux and in charge, we now have many of them which are embodied into the vector x, so again the position, and a vector p, which again the momentum, enabling you to yield this classical Hamiltonian, which is virtually the same as before, slightly more complicated because now we have vectors, meaning now that we have matrices instead of scalars. So zooming in on this capacitive matrix, we can see that we can block it apart into 4 parts. So the network subspace, your cavity qubit subspace. You have also 2 off-block diagonals corresponding to your coupling terms, and a block diagonal matrix corresponding to your waveguide subspace. And what you can see is that you have a diagonal term plus an off-diagonal matrix, which is a function of alpha, and likewise for L-1, but as a function of beta. So it means that we don't quite have the modes of our waveguide just yet, and this is exactly where when the choice of alpha and beta steps in, because as I've said, this remains a general Storm-Liouville problem, so we can choose alpha in order to cross out these off-diagonal terms, meaning leading up to the true modes of our waveguide. So for instance here I've indicated an alpha for a LC resonator, a cavity connected to a waveguide, and for those of you who are familiar with this concept, this is akin to Bogoliubov transformation. So now we just have to make it all quantum, just as before, with the Jaynes Cumming Hamiltonian, but with this time a coupling strength which does carry a natural cutoff frequency. So here it's its general form that I've plotted with what you can see a baiting point. And now, well, it is actually part 2. For some preliminary simulation that I've conducted, considering an excitation initially in the cavity, decaying into your waveguide, with considering the same rotating wave approximation for the ohmic bath case and the cutoff case, what you can see is that the leakage of the photon goes actually slower for the cutoff case as compared to the ohmic bath case, which makes sense because from the bending point, the coupling function of the cutoff case starts plummeting. Now, this is again a very preliminary result, but from the previous decay simulation, we can actually interpolate the value of the decay rate kappa that I've mentioned before. And what you can see is that a form of divergence starts to appear in the ohmic bath, but not in the cutoff frequency case, which is consistent with the previous result. So now, to sum it up, And for some perspective, what we've seen is that we've covered a generalized phenomenological approach to the TE modes waveguide problem in order to end up with a natural baiting point for the cavity waveguide coupling strength. And for some remaining work that is still to be investigated, we still have to understand to better understand the complete state transfer from a quantum unit to the other through your quantum link, and ultimately better understand also the photon shape engineering in these quantum links. So thank you for your attention, and should you have any questions, feel free to ask them.
Hola, hola. Hello. Now? Hello? Okay. Thank you very much, Mohamed. Is there any question? We have one there.
Is there any motivation for putting the cutoff in the?
Sorry? Is there any motivation for?
You do a cutoff in.
I mean, this is the cutoff in frequency that does appear when you do your complete rigorous derivation of your quantum Hamiltonian model. Because, I mean, otherwise it wouldn't make sense, because you would have, for instance, a decay rate diverging over time, which is why I've indicated in the first slides with your G going to infinity, and this is not physical. Which is why in quantum optics we tend to enforce a cutoff.
Nice, thank you.
Any other question? Okay, if this is the case, let's thank Mohamed again.